Welcome to this explainer. You know, if you've ever watched a speed cube or completely demolish a complex puzzle in just seconds, you know for sure there is some serious mental gymnastics going on beneath that absolute blur of hands. Well, today, we're not just looking at the moves themselves. We're going to decode the precise digital tools and frameworks these solvers use to master their craft.
Take a sequence like this: U prime, L prime, U prime, LR, U prime, R prime. I mean, to an outsider, it kind of looks like a typo, right? Or maybe a strange computer glitch. But to the community, this is literally the lifeblood of optimization.
So, what does this code actually mean? Well, this string of letters and symbols is the foundation of the universal language of speed cubing. It's this incredibly precise mathematical notation that solvers all over the globe use to communicate really complex spatial movements. And maybe more importantly, it's exactly what the digital algorithms are programmed to parse.
To break all this down, we have a quick roadmap for today. We'll start with the cryptic algorithm, then look at the dimensions of the cube, the stages of the solve, dive into the SpeedCuber's digital toolkit, and wrap up with reconstructing the solve. It's going to be a fun ride.
Section 1, the cryptic algorithm. Okay, let's dive right into translating this niche jargon.
Now, in this particular ecosystem, an algorithm isn't just software running in the background like we're usually used to. It's actually a physical formula. It's a predefined sequence of moves, like that U prime, L prime we just saw, used to achieve a very specific pattern on the puzzle. And the kicker? It does this without scrambling all the progress you've already made.
And you have to notice how meticulously these movements are measured. The specific base sequence from our source is highly compact. We're talking exactly 7 total moves, but look at how the software tracks it. 7H, 7Q, 7S, 7E. It's capturing half turns, quarter turns, the whole shebang. Every single flick of the wrist is analyzed and optimized for pure efficiency.
Moving on to Section 2, Dimensions of the Cube, where we scale the puzzle.
These digital tools are programmed to handle just an incredible spectrum of puzzles. On one extreme, as noted in the settings, we've got the 1 by 1 by 1. Yep, that is literally a single solid block. It's a hilarious, trivial novelty that obviously takes 0 moves to solve. But on the exact opposite end, this framework scales all the way up to a staggering 17 by 17 by 17 puzzle. We're talking about a massive, intensely complex matrix of moving parts.
I really want you to pause and think about that number for a second. 17. A 17 by 17 by 17 cube. It is absolutely mind-blowing that there are digital simulators robust enough to map out the millions upon millions of spatial permutations on a puzzle of that sheer scale. The background math required to just keep the software from crashing, completely staggering.
And the software doesn't just stop at standard grids, it brilliantly accounts for unique hardware variations too. Take the void cube, for example. Since it's entirely missing its centerpieces, the software has to automatically adjust for that lack of fixed reference points, the very points solvers normally rely on to know which color goes on which side.
Section 3, Stages of the Solve. Let's move to the structured methodology and see how it all builds.
We all know the standard sequential narrative for solving a normal puzzle, right? It kicks off with a cross, moves straight into F2L to pair up those corners and edges, shifts over to OLL to orient the top layer, and finishes up with PLL to permute those pieces into their solved states. The software perfectly maps these standard sequential blocks.
But wow, the rabbit hole goes so much deeper than those 4 basics. Those are really just the foundation. Look at this extended list derived directly from our source material. CLS, ELS, L6E, CMLL, ZBLL. These are highly advanced, super specialized substages that top-tier solvers use to shave mere fractions of a second off their time. The dizzying depth of this hobby is just wild. I mean, solvers will memorize hundreds of these specific algorithmic variations just to bypass or combine a single stage.
Which brings us to Section 4, the SpeedCuber's digital toolkit. Let's look at the actual software for solvers.
So solvers rely on a whole suite of digital manipulation tools. They can expand and simplify their written notation or clean up their code by choosing to remove comments. But the real heavy hitters here, the playback tools like mirror and invert. These settings let a solver take an algorithm they already know, mathematically reflect it horizontally, or even completely reverse it in time. This is a total game changer because it allows them to learn how to execute a familiar sequence from entirely new angles without having to manually reinvent the wheel from scratch.
Then we run into this very specific piece of technical jargon in the options. Hint, stickers, hollow. Let's demystify that for a second. When you're practicing on a flat computer monitor, you obviously can't just physically peek behind the digital cube. So this clever visual interface allows users to literally see through the 3D model to track hidden pieces resting on the back layers. It is an absolutely crucial workaround for visualizing a 3D puzzle on a 2D screen.
Plus, the whole visual environment is completely customizable to match whatever physical cube the solver actually owns. The software natively supports the standard BOY, that's blue, orange, yellow, as well as the alternative Japanese standard. But it also takes custom text inputs. Our source text specifically points out a custom layout coded as GROBY, so green, red, orange, blue, yellow, white. Allowing this level of custom tweaking ensures that when a cuber practices digitally, their visual recognition perfectly aligns with their physical hardware.
Finally, Section 5, Reconstructing the Solve. This is all about sharing the methodology. And this brilliantly illustrates how all of this complexity comes together. It's often just a simple line of code generated by the tool, //view@alga.cubing.net. This brings us firmly back to reality. This isn't just some abstract offline tracker. It's a living, breathing online forum tool where cubers showcase their exact finger tricks and logic directly in a web browser.
Which directly leads to collaborative results like this. 3.47. In our source material, this number represents a breathtaking world record time, just 3.47 seconds to solve a complete, totally scrambled puzzle. It's an almost incomprehensible physical feat of human speed, right? But it's one that is completely enabled by studying, dissecting, and sharing algorithms through these very digital tools.
The end result is this massive, highly interconnected global ecosystem. A solver will use a specific move set, like the T-Soon shape mentioned here, pull off a record-breaking solve, and then immediately upload the reconstruction. That's a meticulous, move-by-move breakdown shared to community hubs like the speedsolving.com forum. And because the backend tools are hosted on open-source platforms like GitHub, the entire global community can instantly download, watch, and analyze the exact mechanics of a world record the literal second it happens.
It really makes you wonder, doesn't it? If this digital toolkit can mathematically decode and teach a 3.47-second world record to absolutely anyone with an internet connection, what other limits of human speed and logic are just waiting to be solved? Thank you for exploring this fascinating hidden language with me today in this explainer. Keep asking questions and keep learning.